I have few stuff to present today. We'll see where we go. So I've been asked to cover some basis of EEG. I will, on purpose, if you want, I can switch to another presentation and go for source reconstruction, but I've been asked to talk mainly about denoising. So I'm going to talk mainly about EEG acquired in the fMRI scanner and what we can do with that. I do have, because this is part of a course I gave in Nice a few years ago, I do also have few slides on basis of EEG fMRI applications, either in epilepsy, in sleep, or in cognition. So if you want, we can go up to there, but we'll see, and don't hesitate because we can adapt. So I'll start with some basics. So you will see I'll skip a bit some slides at the beginning, but some are exactly the same as I did last time. It's just to make sure the physiological basis of EEGs are well known. So first, what is EEG? Of course, it's electroencephalography. It's a direct measurement of neuronal activity as opposed to fMRI, which is indirect by the hemodynamic process. Excellent temporal resolution. We are at the speed of the neurons, typically around 1 millisecond. Spatial resolution is more tricky because it depends. It's a scalp recording, and it's gonna depend on the spatial resolution after the inverse problem. There is no one answer to that, but let's say from 0.5 to 1 centimeter on the cortex. I would say 0.5 is more accurate than 1 centimeter. On the cortex, in deep structure, it's going to be probably less accurate. How do we install? So measuring an EEG, there's nothing difficult. It's just measuring a difference of voltage, a difference of potentials. So you have a reference electrode, and you have your electrode, and you're measuring the voltage between those two. And the standard EEG montage will look like that. So this is the 1020 system, which allows the neurologist to exchange informations when they read EEG. So basically, you put some anatomical landmark like the nasions, the inion, the periauricular point. You make some division of the head into 10, 20, 20, 20, 10%. And then you define this way to position the electrodes. So the name means something: F frontal, C central, T temporal, P parietal, O occipital. Even versus odd number will define if it's on the right or on the left. O3 is going to be on the left, O2 is going to be on the right, and Z when you are in the middle. So what is the signal we are measuring? So I told you these are slides I show you the other days, but I'll just go very briefly. What we are measuring is the summations of some neuronal activity, mainly local field potential, that has been summed over something like that looks like a macrocolon of neurons. We're going to simplify this big macrocolon of neurons by putting one main current dipole summarizing the activity of all that colon. And what is very interesting in the cortex, and it is less our purpose today, but when we are doing source reconstruction, we are using that, is the fact that those colons are, especially those pyramidal cells that we are measuring, are perpendicular to the cortical surface. So we have all the cells that are perpendicular to the cortical surface, and we are using that as an anatomical constraint. And so this is also why it's going to allow some summation of the activity that we can record. Again, I can summarize. This is just to summarize one dendrite of one neuron. So you have an action potentials coming, a flux of ions inside. This flux of ions will generate a magnetic field. So if you have the current like that, the magnetic field is rotating around. And then you have volume conductions current outside because you have ions outside to close the loop. And that's going to generate EEG. And that's also the reason why EEG, you need an active conductive contact to measure an EEG. So all of you who have installed EEG knows you need to gel and to make an electrical contact, which is not the case when we measure MEG, because we just need a coil to measure a magnetic field. And so we summarize this, or a macro column of dipoles oriented like that by one current dipoles. And this is just the main formula saying that the electric potentials of the magnetic fields estimated here at a specific distance from our current dipoles depends either here on the dot product between the flux here and this distance, or on the cross product for the magnetic field. So this gives rise to this famous representation of, if you have an a current dipole here, the voltage is going to be 0 here because of the dot product, maximum here, negative here, and this is the magnetic field that rotates. So that's what we are measuring. It's not all the neurons, it's mainly the pyramidal neurons because they are nicely perpendicular to each other, but parallel to each other, the dendrite and the different neurons, as opposed to the interneurons, which has more like a kind of a stellate shape. So if you have a dipole on all those dendrites, if you sum the vectors of all those dipoles, even if they are synchronous, they will not show a resulting field. These are simplification. It doesn't mean that we might not have a little bit of this information, but in general, we say no. And then when we looked at those pyramidal cells, the excitatory synapse, so typically, let's say more glutamatergic, it's going to be here on the apical side, and it's going to generate some negatives here, whereas the inhibitory synapse, more GABAergic, will be here and will generate a positive current here. So at the end, it's generate a current of about the same, but what's important is that you have a sum of excitatory and inhibitory postsynaptic potentials that's going to either hyperpolarize the membrane, and then it will not be excitable, or depolarize the membrane. And when the depolarization goes above a threshold, the neuron will generate an action potential that's going to propagate at a distance through the axon. And yeah, so this is just summarizing here. So this is the main activity. We have our current dipoles perpendicular to it, and we're going to record EEG on MIG. So let's look at some signal here. So here, these are just two standard systems. So I guess some of you who have installed some in the scanner have been used to that one, which is just gluing 3 electrodes directly on the scalp. That is still done clinically in many centers. At the neuro, it's done every day with the minimum electrode, which is 19, 10, 20. We usually ask a little bit more than the 1020. We ask for the lower temporal electrodes because the 1020 is really not covering some part of the temporal lobe. And that's also a problem with some of the commercial EEG cap that you see mainly for application in psychology. Some will stop there and you are really losing some. So now most of the cap are more high density and they will cover nicely all those regions. This is an example, a bit old now, they have better system now, of high density. This is with 256 electrodes. At Perform, we have a similar system that is actually MRI compatible. And this is an example of a background EEG where you see all your EEG line. And here you see the time resolution. You have basically 1 second between 2 vertical bars. Okay. So I'll ask the neurologist in the audience not to say anything. And can you tell me what you see on that EEG? What is this? Is it artifact or not?
Epileptic seizure?
Not at all. This is the first thing you do when you record an EEG. Yeah, where do you see the eye blink?
Yeah. It kicks.
In the middle, yeah. So here, this, and this are eye blink. So then what we see before and after the eye blink? Yeah, we see a lot of alpha activity. We see alpha activity here. So when are the eyes closed and when are the eyes open? Yeah. So this is typically what we call the alpha reactivity. So when you install an EEG and you want to make sure it is correctly recording, you ask your subject to relax, to close his eyes. It's going to generate some alpha activity, mainly occipital. If you ask the person to open, of course, you get an artifact because of the eye blink, and you should see some beta activity. So here the person blink 1, 2, 3, and go back to alpha. Relax. It's not always the case. Some people are more stressed, and there are some are not generating that much alpha. Some are generating alpha even eyes open, but that's the basic idea. Like recording a good alpha eyes closed is a good sign that you have a decent EEG. And so this is just another example. So this is EEG awake, where you see here the eyes closure. So this big eye blink. And I'm mentioning this because this is important when we do analysis, whatever is the analysis, because eye blink, we have good tools to remove it, but an eye blink is very high amplitude compared to many other signal of interest. So it's easily 5 to 10 order of magnitude compared to, for instance, the evoked potential. If I'm doing a visual evoked potentials, and if I have an eye blink, the eye blink will be 10 times larger. So if your participant is blinking his eyes each time you show something, it's going to be difficult to get your response. You can always clean using post-processing, but it's also good when you make the design to allow the persons to blink. So you say, okay, during the task, please avoid blinking, and then you make a cross stop or something, and we let you a period of few seconds where you are allowed to blink. So then we don't need to wait too long because we know the response to brain activity is in few hundred milliseconds, so it's very fast. Of course, when we do EEG, one of the typical study, and several of us are interested in that, is to study sleep. And I don't have slides on that here, but as many of you know, sleep is completely defined, characterized through the EEG, the different sleep stage and all that. So what you get in general in sleep, in deep sleep, is that you have some slowdown. So the rhythm is at lower frequency, and because it's at lower frequency, it's easier for the neurons to get synchronized. And when you get synchronized at a lower frequency like that, you get a stronger signal. Just the image I like to show is the image of people clapping in a stadium, and if they clap like that, you get a very nice noise. If they clap like that, it's going to be just nonsense. So here you have some slowing of the activity, and you have I'll go back to that later. One typical signal we're highly interested in sleep, which is a sleep spindle. And this is linked to memory consolidations, to training, and so on. This is an example of an epileptic seizure, patient sleeping, you have few eye blink, and then you see some rhythmic activity that is starting there. So there are a lot of different epileptic seizures. What is important here is this rhythmic activity that you see. Probably at that time, the patient is not moving that much, but if the patient will start moving, especially you might have seen some seizure where they move the head or things like that, or they jerk, your EEG is gonna be completely contaminated with muscle artifact. So it's gonna be quite difficult to analyze. So when we analyze seizure data, we usually analyze the early phase of the seizure before they move. It depends on the seizure. For some, it takes few seconds before they start moving. For some, they move right away, and they moved a lot. So sometimes it might be quite difficult. I was mentioning that, but that was another purpose, because I like to show that our source reconstruction is associated to spatial extent. It is sensitive to spatial extent. But this is just to see that the main signal we're looking for in epilepsy are those which we call spikes or interictal discharge. So there's a little lump, like it seems to be a problem of imbalance between excitability and inhibition, but it's not a seizure. And so the patient is not aware of having that. And it's cool to measure this because you can measure this with many different tools, localize them, and that gives clear information for when you want to treat. And just I wanted to say, because this is a nice study when they record this with intracranial EEG, and when you see those spike outside of the noise, so it's really a good SNR data, it means that you have really a lot of stuff inside to generate such a strong SNR. If it was just one tiny contact with a little blip, we would probably not see anything on the surface. So because it's an EEG fMRI class, I mentioned fMRI. I will go rapidly on that because I assume you all know what fMRI is, but as opposed to EEG, fMRI is measuring hemodynamic activity, mainly because through variation of deoxyhemoglobin, because deoxy is paramagnetic, so it's going to distort the magnetic field and you get your signal out of that. Actually, it's a bit more complex than that. It's a combination of blood flow, blood volume, and deoxyhemoglobin. Temporal resolution, it's changed. This slide is a little bit old. I put 1 second. You now have a sequence that can go, I would say, probably around 200 milliseconds. The TR, or some standards old sequence that are around 2 seconds for TR, and a spatial resolution of 2 to 3 millimeters. And then you're going to design a task. So typically a block task off, on, you record your signal, and then you hope that your signal is following your expected model, actually convolved by an hemodynamic response that is peaking 5 seconds after. So we are really, like, what I want you to remember is we are really delayed in time. We have the EEG that responds in few milliseconds, and then you wait 5 seconds before getting your fMRI signal. So if you get a strong propagation from a region A to a region B in 100 milliseconds, then you pass a very smooth temporal filter to get your hemodynamic response out of it. So the timing, for instance, I don't believe much in Granger causality in fMRI signal because of this effect. You might see big trends, but all the fast propagation you see in the EEG, there is no way we can catch it through slow hemodynamic process. And then you can make a map. This is the typical shape of the fMRI response. I'll skip that because this is all known. So blah, blah, blah. Yes, and you can do event-related design as well. Okay, so now let's go to simultaneous EEG fMRI. And so the idea is to combine those two modalities and just to say that. So we're going to combine those two modalities, and there are some rationale why we should do that, because you should think before doing it, because if you can do a very clean EEG only experiment and then a very clean fMRI experiment, it's better to do them separately because putting them together creates a lot of problems. So you only do it when you need it. And there are not so many cases, but there are a few cases. So what you need to do is to make the link between EEG and fMRI signal, which is the so-called neurovascular coupling. This is usually done by extracting some EEG features and convoluting with hemodynamic response functions. And then we can perform a correlation or general linear model to find out which voxels appears to have an hemodynamic signal that is linked to this specific signal we extracted from EEG. What is this signal? It might be an epileptic spike or a seizure, as I showed you. It might be a sleep spindle. It might be a global rhythm. You might want to model the fluctuation in alpha, but the fluctuation of alpha is, I would call, instantaneous. If you want to see the brain, the hemodynamic response to alpha, you still need to convolve by an hemodynamic response, because if you have a peak in alpha here, it's going to appear in the hemodynamic signal 5 seconds later. Should we expect EEG source analysis and fMRI to be exactly one-to-one correspondence? The answer is no, because we're not dealing, there should be some level of correspondence, but not a one-to-one. So EEG and BOL are primarily driven by postsynaptic potentials, but the main difference is that EEG is mainly driven by synchrony. You have different generators that are in synchronicity, and you're going to get sufficient signal. And to get synchronicity, you might not need too much energy. Yes, and one of the most common example is generating an alpha rhythm doesn't require that much energy. On the other hand, to get a strong bold signal, it means you have a metabolic hemodynamic answer. So why we have more blood flow coming there? Because there is a need for oxygen, and there are some mechanisms to bring the fresh blood there. So it's not exactly the thing. So you can have some strong signal that requires energy. So it's going to generate a high bold signal, but we have very little EEG signal and vice versa. EEG is also really driven by the anatomy, so by the cell orientations. So as we said, if you have a closed field, you will not see EEG, and you have specific patterns depending if you're in the sulci on the gyri. Bold doesn't care about that, but bold will care about the underlying vasculature. There are issues whether the bold is too much influenced by the veins or is it really neuronal activity. Of course, bold you measure more or less, I would say fMRI spatial resolution is the same everywhere. A bit better on the cortex than in the center, but overall it's the same. EEG is clearly measuring mainly cortical activity. Getting access to deep activity from EEG, it's a big challenge. Actually, with the recent paper of Jawata, we show that it seems possible in some cases when the signal to noise ratio is high. But as we will see in a minute, the issue of EEG in the scanner is the low signal to noise ratio. So getting activity at low SNR in the scanner is the most difficult part. So what are the main? So this is a non-invasive examination of the whole brain. It requires EEG to be recording in an MR scanners. And if you think about that, EEG is measuring electrical activity. So the worst environment you want to record an EEG is in a huge magnet. But despite technical difficulties, it is possible and we can denoise. And I'd like to start. So this is courtesy of very old slides from my friend Christian Bénard from myself. And when he first developed that, it was not a machine to make sausages out of a subject. But so the idea here is that we record EEG inside the scanner. So we need to have electrodes that are compatible. Most of electrodes are made with silver, so there is no problem of compatibility with magnetic field. So 25 more or less, so 1.5, 3T. I think the lab of Zheng Shen and the lab of Jean Gottman, they're going to try their first EEG fMRI at 70 at the end of the month. As I will show you, the main issue we have when we record EEG in a magnetic field, what's happening if you have an electric wire that you move in an electric field, in a magnetic field, you're going to generate current by induction because the flux of magnetic field change, so you're going to generate. So you want to limit the motion as much as possible. And the highest you go in field strengths, the strongest will be those motions. So we started at 1.5. Now most of us are using 3T and even worse at 70. So that's why you try to minimize the motion as more. So a typical good tool provided by Siemens, I don't remember if we have that at Perform. It's a cushion that is made with styrofoam spheres, and then you make the vacuum out of it, so it fits exactly your head, and then you're stuck. There are other ways that you can put stuff but try to maintain the head so that it's not moving to its maximum. Usually you have the electric wires that goes out directly. Ideally, but it's not always the case, it should be from the back. And we had issue because that is problematic, like some of the most advanced coil that have been developed for fMRI are not developed for for EEG. So we had the case where we had to put the wires in the eyes, and I think that's what you've been experienced. But ideally, the wires should go there. Now, there are some companies who are making coils a little bit more dedicated. There, we preserve that. A very good one I'd love to try one day, which is coming with the most recent GE system, is they have a kind of coil which is adapting to different head size. So you can really open between those two. So that would be really, really appropriate to pass the EEG system. So then what are those? So they are not sausages, of course. These are sandbags. So we put sandbags on the wire. Again, it's to limit the vibration. Limiting the vibration gonna limit the noise in your signal. You have the amplifier. Usually it's just outside the tunnel. So these are specific amplifier that are shielded. You don't put any amplifier in the scanner. It has to be an MR compatible amplifier. So brain vision amplifier are very good ones. We also have EGI system. I think the brain vision one is better. And outside of your amplifier, you have the signal is coming out of the fMRI room through an optic cable. So it's fiber optic there. So then the signal becomes optic, so we have no problem anymore at that. So the machine to record the signal is outside, is usually in the control room. You need to make sure you have a very good synchronicity between your signal, and it has to be a very rapid synchronicity and not one at 200 hertz. It has to be way faster than that. I'll go back to that. So typically, we are using a sampling rate of 1 kilohertz to 5 kilohertz. EGI is limited to 1 kilohertz, and I must say it is a little bit limit. 5 kilohertz is better because you want to catch this. This is typically what we call your gradient artifact. So what is your gradient artifact? You put your subject in the scanner, you start recording your EEG. Your EEG is of decent quality, I would say. Now you start acquiring your sequence. Whatever is the sequence that you used, you know an fMRI sequence will change the magnetic field by applying gradient. So it's the same idea as moving a wire. If you change the magnetic field, it's going to create a current. And because you change a lot those magnetic field, the current that you're generating is huge. And this is what you can see here. So this artifact is actually gigantic. So that's why you need specific amplifier. First, you want an amplifier that has sufficiently, over the time, but we don't want saturation of the signal. So you have to have a good dynamic range. And then you want to have a good sampling rate because you want to catch this very fast change. If you would sample that at 200 hertz, you would never catch those fast change correctly enough, and you will need that correct. So that's why when it became, I think the first was at the end of the 90s by Ives. So when the first amplifier became, they rapidly measured, increased the sampling rate and the dynamic of those amplifiers to record a decent EEG signal. There have been a lot, I will not cover that. It's become a real critical issue at 70. There are issues on safety. Of course, you don't want loops. You don't want those electrodes to start heating. One typical technique that has been proposed by Brain Vision is to add a little resistance to each electrode. So which means that the impedance is going to be a little bit higher. So you need to take into account. It's not all the systems who are using that. I must say, with lots of experience in Jean Gottsman's lab, where we use just standard electrode, we never had any issues with heating or problems like that. At 70, you'd better be careful. It depends also on the sequence. I remember when for your study for the MRS, because MRS is not depositing the same energy as a standard Bolt signal. So that's not my expertise, but I remember Makoto checked some aspect on that. So this might be important. So then we're going to review that because what you need is to denoise this EEG. So you come with an EEG that is slightly of better quality, and then you try to do something with your EEG. And depending on what you need to do, it's you have different stuff. So what are the source of artifacts in the MRI room? So it is challenging. So what are the source? So the first thing is the movement of electrical equipment. Each time an electrical equipment will move, it's going to generate a signal. So this is why you're going to use sandbags. You're going to try to minimize the vibration to its maximum. And of course, you have this gradient artifact. So this is a gradient when we had, so depending on your sequence, if your sequence has a gradient with a stop, like you say, you acquire one API volume, you had a little stop and then acquire a second one, which is more the old way of doing, you will see a pattern like that. If your sequence is a more continuous without gap fMRI sequence, it's going to be a continuous artifact compared to the EEG outside the scanner. So this is the huge artifact. The cool thing is that this artifact is really linked to the sequence, so it's really reproducible and not so complicated to. The other issue, so the main solution, we'll see it's average artifact subtraction. So the other issue are the helium pump. So the helium pump's gonna generate some artifact because it has some oscillations. And you need to have this pump helium for safety issues in the MRI scanner. So really, fMRI technicians don't like us because we would like to stop that for some moment, and we should, when we do it, we should be careful of switching it on when we're done, otherwise they will really not be happy. And the main issue here is that this is really for more high frequency noise, so 40 Hertz and above. If you're looking for high frequency activity, like challenging gamma in the scanner, with the helium pump on, just forget it. It's going to be completely overlapping.
Does it support the helium pump?
It's cool.
Yeah.
And it's in case, yeah, because you see it's full of liquid helium inside the coil to cool, because it's the MRI magnet is a superconducting magnet. So normally you should not, like, it's closed, so but it's for some safety issue. And the last point that we'll see, which is not clear, but very soon, and especially was not so clear at 1.5, but when we switch at 3 Tesla, it became really huge, is that when you start denoising an EEG signal and you look, it will look like that, blah, blah, blah. And this is an artifact that will occur at every heartbeat. And this is what we call the ballistocardiogram. And the origin of that was, now we know better, but it was not so clear at the beginning what was this. And we have different solutions. No, not perfect. We try to improve that, but we'll see. So let's look at some real data. So these are EGI data acquired at Perform on the 256 system. So this is the raw data. So during an API sequence, so of course you don't see much. We're going to remove the gradient artifact. So I'll show you in a minute the gradient artifact, because it's so reproducible during a specific amount of time, because everything is nicely synchronized. You just create a template, you average the template, and you're going to remove the template. And then you start seeing this ballistocardiogram at every heartbeat. So after correction of the ballistocardiogram, it is better, but still probably not perfect, and we might have. So I have a few examples here. This is just another example, EEG with artifact after subtraction. At the very beginning, some techniques they've been using some filtering in Fourier, but that was not perfect because the band covered by the gradient artifact were not so, they are narrow, but not so narrow. And this is also the EEG in the scanner when it's not scanning, which is a good tool to use because it's not so bad, but you still have the ballistocardiogram. So, yes,
ECG to reach the balistocardiogram.
I'll get to that. That's the next slide.
Okay.
I would say yes. So, what is the balistocardiogram? It is linked to the ECG. It's linked to the cardiac. And so you know you have when you have a cardiac pulse, it's what we call the QRS. It occurs more or less every second. So this is what you measure with your electrocardiogram. And of course, there is a delay because the electrocardiogram is measuring electrical activity here, and then you are measuring something here, which is a little bit different from, for instance, people who are doing MEG or sometimes high-density EEG. They are measuring EEG artifact, ECG artifact, cardiac artifact in their signal. So when we do with Jawata, when we do resting state connectivity in MEG or not, we are removing the cardiac. This is more an instantaneous cardiac signal because it's just you have a strong dipolar field here that's going to be measured by electrodes. So that is instantaneous. And we have technique to correct for that. That's not the, like most of the time an ICA will correct nicely. It depends on your subject because if you're smaller, your dipole here is getting closer to your electrode, so you will get a stronger signal. Here it's a little bit different because we have a delay. And for EEG, it's a long delay. So when you have the QRS peak, so the cardiac pulse, the artifact we see on the EEG is occurring between 200 to 400 milliseconds later. So it's not instantaneous. And that makes it a little bit more difficult because of its variability. So it's more variable over time than the gradient artifact. And this is why it is a bit complex. So what are the main hypotheses behind that? So there are several hypotheses, and I'll show this study from Karen Mellinger from UK, who I think find out what's the main thing. So the main idea is that perhaps at every heartbeat, you have a little rotation of your head like that. You might also think of a Hall effect due to the pulsative blood flow. So electrically conducting fluid in a magnetic field. So this is creating a Hall effect. And this will create a difference of electrical potentials. Something else that was mentioned is pulse-driven expansion on the scalp. If you assume your electrode is there on the scalp and you have a little vessels just behind it, when you have pulsativity in the vessels, the electrodes will slightly move like that. And we are talking about tiny, tiny motions, but at 3 Tesla, it's going to generate a fluid. And actually, and I'll show you in the next slide, it's head rotations that seems to be the main contributor. I don't have the slides here, but probably 15 years ago, there was a very nice paper from Pierre Levent, a former student of Jean, where they used something to track very tiny motion of the head in the MR, which is what we call the moire figure. So it's a kind of receptor you put on the front. So it is like a some stripes like that. But when you move them, it's changing a lot. So with a little camera to catch it, you can catch really, really tiny motions. It's like a motion detector that you can put. And actually, it's very nice because you can synchronize your fMRI scanner to that to follow. So they've been showing that if you do that, the scanner can follow you. But not all systems can do that. But what Pierre showed there is by doing that, he recorded the ECG, and then he amplified the motion. And then he showed specifically that we really had a motion like that after every heartbeat. So it's tiny, but there is. And actually what Karen did in that studies, so she tried different effect. And what she did is she recorded this ballistocardiogram. So basically each time she has a QRS, she's recording the EEG signal, and then you can average your different QRS and you get your response. So you say most of the artifact is coming here around 200 to 400 milliseconds. And this is when your subject is relaxed. So if we go from the 3 hypotheses, here you have all the 3 hypotheses together. So it's perhaps rotation of the head, Hall effect, or expansion. And so what they tried, and this is still a solution they do, which is quite useful, is they are insulated some electrode of the cap. So typically, if you have an EEG electrodes like that, you can have an electrode that is not touching the skin, that is touching some plastic or whatever. So that I think it has to be a bit wet, but that electrode is not measuring your brain signal, but just noise. But if it's moving, you're going to catch something. So this is a very nice technique to correct for EEG artifact. The only thing that I found a bit bad is that she's using an high-density EEG cap, and then she's leaving perhaps 10 electrodes as active electrodes, and all the others are insulated electrodes. So at the end, you don't take benefit of the high density, but you denoise very well. These are fMRI people, not EEG people. So the other things that they did is they use a bite bar to constrain and a vacuum cushions to really reduce the motion to its to the maximum. And so this would only remove the rotations. And then they combine the two, so the restrained and insulated cap. So if you don't move and if you don't measure EEG, the only things that should remain is these little expansions due to the vessels. And so you see very clearly that the main effect here, it's small, the main effect is there. So you see that the main effect was due to rotation of the head. So that was, so this is what we know. So few methods, basic methods. So this is still the main method that has been used and that is still being used. It's old, you see, it's 98. It's still being used as the standard method in all EEG fMRI software. So first, the gradient artifact is measured by averaging the artifact and subtracting it. And you can do the same for the ballistocardiogram. So you take every QRS, you record your signal, you make a template, and you remove, you average, and you remove from it. So it works so it's a channel-wise artifact subtractions. So we use an average template, and you need to define a time window to do it. What is absolutely required for that is a high sampling rate and a very good MR to EEG synchronization. So it works very well for gradient artifact. That's still the reference method. Doesn't work so much for ballistocardiogram because of the variability, the response. So that's why those people, a few years later, so 2005, proposed to use optimal basis set as a technique to do it. So the idea is you detect the QRS timing using a more or less robust estimator, but you need a good, in all those cases, you need a good ECG. You shift all the QRS by roughly 200 milliseconds, and then you're going to model the temporal variability of the response. So you're going to fit a PCA model here, and you're going to detect the first 2, 3, 4 components to try to model the fluctuations of the response and to do it. It is working. It's a little bit difficult to tune on some, but you can fit on this. So this is some examples. So this is not using optimal basis sets, but this is slides from Christian Bénard. So of course, there will be ICA there. And so you see the EEG here with all those ballistocardiograms that you see very nicely here. And this is a correction from PCA, which is not bad. And this is a correction from ICA. And in your ICA, what you see is that this component, this component, this component, and this component is clearly seeing this repetitive rhythmic pattern. So it looks like it was not only one basic component, it was a little bit more, and you can remove those. And this is actually working nicely. Usually, like one of the standard technique we are using is we first use AAS, or OBS. So we first remove most of the artifact. We look at those, and when we realize, looking visually, that it's not so difficult because you see the repetitive pattern, So then we had an extra level of ICA. Those techniques are always a little bit more challenging because when you remove patterns from ICA, you want to make sure you're removing only the artifacts, so you never know. So when it's pure resting state and it's really correlated with your cardiac, that's perfect. When it's more like, for instance, if you have a task and then if you have a motion associated to the task, those can be a little bit more difficult. And here you have an example of how it has been. So you have here the original data. You see 3 epileptic spikes, and then you see plop, 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 which are the remainder of the ballistocardiogram. And it has been here nicely removed. We still see a little bit from the PCA, and we see clearly less here. This is a study that was done by Stefan Ebner, who's considered as really an expert in the domain for applying EEG fMRI for cognitions. And he compared different techniques. And it was done using auditory evoked potentials. So it's looking at the amplitude of the evoked potentials in different conditions. So he found out that applying ICA reduced the SNR and the amplitude. OBS or OBS combined with ICA, you improve the SNR. So they were looking for the N1, so the 100 millisecond response after an auditory potentials. This is another paper, similar stuff. This time it's visual evoked field, and they compare either OBS, optimal basis set, ICA, or the combination of the two. So they find out that they yield similar result, more parameter tuning for ICA, which is always the problem with ICA is which component and how many components to remove. So that's still one. But you also have a choice of number of components for OBS. And so the combination of the two is possibly good, but the additional effect of ICA is subject dependent. And that's what we do in practice. We have subjects that are clearly more noisy than others, where we decide to add this ICA step after the standard technique. Yeah, you can look at different, here they look at different components. I will just go now to one last technique, which is a study which will go back to the quality of the EKG, which is a study that was done by Makoto. And so you have, again, your MRI gradient artifact, you removed by AAS, you get this. So you see here your ballistocardiogram, you see here our EKG, not the best EKG ever, but this is typically what you might get in the scanner, depending on how you install your electrodes. And so you see an example here. So you can remove, try to remove the ballistocardiogram using also the AES method, so by just averaging. So it works somehow okay. And so in this study, so this is a sleep study we did with Makoto. We were interested in measuring those spindles in the fMRI. And what was really problematic is that those artifacts that we are getting linked to the ballistocardiogram are really overlapping with the spindle frequency band. And that makes them quite complicated. I don't know if you see it here, but here you see some artifacts, and here you see what, according to the expert, has been considered as a spindle. But you see it's not clear, and even our experts were not. So this is after AAS subtractions. Of course, if you don't consider any AAS subtractions, it's even worse. And try to find out where is your spindle here. It's completely impossible. So then what Makoto did is he averaged several spindles, and he made time frequency representations. So here for few electrodes, you have time frequency representations. And you see here, when you apply the AAS method to correct the ballistocardiogram, So we still see some remaining artifact over there, but we see mainly a nice peak here between 10 to 15 hertz. So we are more or less in the spindle range. So this was considered as okay. This is a group level change level at 20 subjects. And of course, if you compare artifact BCG corrections and no BCG corrections, when you have no BCG correction, all the power goes there and you get almost nothing in your band. So you see that. And of course, you also have transient. So this is why you have this bands that goes to some high frequency over there. So that's a little bit where we are. So this is where with Makoto, we decided to do something else, inspired from what he did with Matt Brooks in UK. So we tried, because we have high density, we tried to apply one source reconstruction technique that is known to denoise a lot the signal, which is called the beamforming. So beamforming is a spatial filter. So basically, we're going to use the combinations of all those sensors, and we're going to try to find the combinations that's going to try to localize, generate the signal from one specific regions. And when we do source reconstruction, we're going to do that for different regions. I'm not specifically a big fan of this as a technique for source reconstruction. It has limitation, but what is clear is that it's an extremely efficient method to remove artifact. Why? Because you try to create a spatial filter that generate the activity from here. Your artifact is coming from somewhere else. So finding a combinations of parameter to remove the artifact is very efficient there. Perhaps you might have still source reconstruction issue, and choosing where you put what we call those virtual electrodes is an issue, but there is something else. I will not talk much about that, but that's something very interesting that we did manually. It's Zhengshen who did that first. As you can see here, there is a loop here, and actually we have 4 or 5 of those. This is what we call a carbon wire loop. So this is another technique that we use to measure artifact only. So if you put a loop in the scanner, it's a loop of it is a loop conductive. So if you move slightly, you're going to change the flux of magnetic field, you're going to get current. So this loop is, of course, not getting any EEG signal. So this loop is only measuring the motion. And using that to correct for ballistocardiogram is also quite efficient. And it can correct for other motion, so it is. We use carbon to avoid heating, because of course, if you create a loop, you might generate heating. So that's why. And this is working nicely. I know the team of Jean Gottman is using that and is comparing the signal from those loops to the signal where it presumed to be an epileptic signal. So if you say, oh, this looks like epilepsy, but if on the loop you see the same signal, you're sure it's an artifact. Then the technique to denoise the signal, there are some GLM techniques that have been proposed, but I think they can be. So this is for carbon wire loop, but I will mention now the stuff of Makoto on beamforming. So what Makoto has been doing, first he tried the effect on the ballistocardiogram artifact. So here these are time frequency representations from all the electrodes. So here what he just did, he averaged the ballistocardiogram effect. So he took all your QRS, he created all the time frequency map, and he averaged them. So you see that when you have no correction, you get a very strong signal you see the oscillation. It's a strong oscillations that you see. Some of the peaks should be around here, around 400 milliseconds, but that's what you see. This is what you see when you subtract using the subtraction method. So the artifact is still there, but in terms of intensity, it has been extremely removed. So this is where we are. And then we applied our beamformer. So we have our beamformer map here. So here we looked at one virtual electrodes that we put here. So we looked in these locations because we know this is an important regions where spindles are generated, because we were interested in spindles. And when you look at the average ballistocardiogram in that regions, you see that it's actually we make the statistical test, it significantly decreased even compared to the smaller method. So that was a nice way. Of course, I'm getting the signal from one region of only, which is that regions. Of course, I can redo it to another regions. I don't know how it's going to behave in other regions. And there is one idea of putting one virtual electrodes below every electrode to kind of, it's not generating another EEG signal, but so if you look at that, when you have the, yeah.
So can we reconstruct the signal at the EEG sensor after removing the noise using beamformer? Or let's say if we want to use another source localization technique after.
Yeah, it's not that clear. Like this is typically what you do with an ICA or with a PCA. Here it's not that clear because here I have the signal only from one locations. So how do you go back? Because in terms of the spatial filter is a linear operation. So you have all your sensor that goes to your linear. Technically, yes, I would say.
Or should we do
Yeah.
that for like the anterior cortex?
But you need, you
will
need to rebuild your MRI. You need, like, the thing is that if you generate, because you have a W matrix that is mixing the stuff, so that matrix will remove. Now, if you go back, there is a chance that this matrix, if you go back, will re-amplify the noise.
Okay.
And the other aspect is that if you want to regenerate an EEG signal, you should not do that for one locations, but for all locations. And what are all those locations? So that has not really been done. This is something we started discussing with Makoto because I wanted to combine that. So my questions for Makoto that we never did is that if we do the same, but with a more optimal real 3D source reconstruction, not only a spatial filter, but we never went there, but that's a possibility that could work. And just to give you an idea, so this is the kind of time frequency map for the detected spindles by our expert after standard corrections. And this is what we get for using beamformer. So here you see that we removed also some of the low frequency noise here, and we have really only our peak in the spindle range. So that was really nice. And the last thing that Makoto did, I will not go, I think he has more, these slides are a little bit old. So he used these patterns to try to model the amplitude of the spindle and to see if the amplitude of the spindle is modulating the fMRI signal. And it looks like slightly here, we found a slightly smaller regions when we are modulating. He has more recent results. This is now a paper in revision. So yeah, that's it. But if I want to look into that, what are the main limitations is that when you look at your EEG, your EKG in the scanner, it might look like that, which would be just perfect. And that would be perfect for AAS methods or OBS. But sometimes it looks a little bit more like that. And then you are a bit stuck. So there are techniques to be a bit more robust. So ECG signals is distorted in the scanner. You might have distortion, some variability. Semi-automatic detections of the R peaks are not that well. So we are using it. Usually what is done in John Gottman team is they detect automatically the R peak, but then they are making manual corrections because some might be missed by your algorithm, and it might be subjective and not always reliable. So just to conclude on why using EEG fMRI, so where we want to study, sometimes we have no choice because we want to study spontaneous or transient discharge. So basically we have no task and we want to evaluate something that has been generated by your brain. So EEG is absolutely needed. And this is the main two applications are actually in sleep, like looking at spindles, slow wave, or in epilepsy. Or you might want to study some background. So you might want to study resting state in different specific bands. So you need the two. And you might want to study connectivity, multimodal connectivity. So then it's better to use them. So there are a few papers, notably in Geneva, that they are comparing the connectivity in the EEG versus connectivity in fMRI, knowing that we are measuring two different beasts there. And it's been used, but you need very specific application there for specific applications in neuroscience. And here, for instance, if your basic task is a basic finger tapping, there's probably no good rationale of using it simultaneously, because you're going to get better signal in the two separate EEG only versus fMRI only. But some tasks, especially when the attention is very important, if you redo or if you have some habituation effect, if you redo your experiment in EEG and then in fMRI or vice versa, you might change the response, or you might change the effect of attention. So this is where it's been done. So typically there have been some study looking at the P300 response and looking if the P300 timing is correlated with your fMRI and so on. So it's already more than 1 hour, so I'll probably stop there. And
maybe we have one or two questions.
Yeah.
Yes.
Thank you very much for this very nice presentation. So I was wondering, I was hoping to get some information, like what would be your advice about the pipeline or about the toolboxes that we are implementing on the data in the case that we are practically working with the signal. So I've been jumping between the different applications, but at the end we deal with residuals of an artifact or ECG artifact. So I was wondering what would be your recommendation?
So as I told you, I'm not aware of typically what are specific toolbox for Brainstorm or whatever that have been implemented for that. Like here, I give you more of the generic tools. Usually, most of those tools, like the BCG removal, are actually in our practice. We are using those implemented in the software, like in Brain, for instance, Brain Vision is doing a good job. And I think in your data was Makoto who prepared that. So after what else you need, it's also really depending on what is your questions. And so what kind of response? It's not the same if you're looking for, so I give you the example of Makoto, which was an example dedicated for spindle. But depending of if you, what you need to do, I think you have to be aware that getting accurate eye resolution in the scanner is tricky. Getting gamma is very tricky. And try to, as much as possible, I would say, try to get some, and that's true for any EEG analysis, is before finding the most tiny or effect interest for neuroscience, try to see how accurate you can detect something that you know. If I show you the basic studies, you have the reference there that were comparing different methods. They were using very basic tasks. They were using the first ERP response on a visual task or the first auditory response, and they were looking at the amplitude and things like that. So these are so we really like, there is no one pipeline in EEG. The pipeline will be dictated really from, there are some good practice. There are good tools in Brainstorm to remove cardiac, to remove eye blink and things like that. But yeah, I think it's really a question of where is your, what is your objective?
Exactly, I want to say, okay, let's say we use the brain vision analyzer to remove the gradient artifact and BCG, we still have residuals. And I use ICA. Again, ICA is not like 100% isolating the noise. So we just ignore the rest of it.
Yeah, we've been using ICA there. There is another study done right now, which is showing that AES plus ICA still seems to be, like with Stan, we have a multicentric studies where it was not on that, it was sleep stage scoring. And then we apply different combinations of corrections and we ask people to do the sleep stage scoring. And then we looked at the reproducibility. It looks like the most basic technique, which is still AES or AES plus ICA, seems the most relevant. The beamforming has not been implemented in that one. I wanted it, but we did not have time. And OBS might be a bit more tricky to get. So I would start on that. But yes, you are aware that you have some residuals, but then it's more questions of what you do after, and like it depends. When you look for epileptic spikes, if you see that your residuals is at the same time, if you're in epilepsy, it's not that complicated because we're gonna look for epileptic spikes. If I see that my epileptic spikes occurs right on top of an EKG peak, I will just not select it because the risk of being an artifact is very high. So, but that's specific for this study. So we can discuss that in your case, means what's your hypothesis, what's the parameter you want to extract from your EEG, and then we can try to find out what's the most optimal set.
Yeah. I think that the underlying idea is to link between the amplitude or the power of the signal we have in EEG and the related GABA or glutamate concentration that we have. So this is the main idea. We have some like hypotheses saying that when you increase the glutamate, you have more pyramidal cells are activated. And if we have more activity with the pyramidal cells, it means that probably the power is more higher. So that's the main idea for making this relationship between the power and the concentration.
I assume if you do that, you're going to look for an envelope in a specific band.
Yes.
So more likely, if you go in alpha, perhaps beta, you should not be too much. It should not be too much of a problem. And then you look at your signal because the fluctuations you're going to look of your envelope, those fluctuations are quite slow. And what I already mentioned, it would be great in your experiment because you have the EEG attached. If you find sometimes in the protocol to acquire that in the scanner, but to acquire that also outside, because like if it's acquired outside in the next hours, to me, I believe it will not change. It might change more at a longer range during your day, but just at that time. So just, I would say, as a sanity check, making sure that the kind of correlation, the kind of envelope fluctuation spike trends you are getting in the scanner and outside, that would help. A key idea in EEG, it's always when you start, it's look at your signal. Because if you have a very strong artifact, a very strong noise, let's say muscle activity at that time, it might create a huge envelope over there and you might completely. So if you see that on your data, this would probably be a part of the data I would remove. I would start on clean data, even if you have some residual ballistocardiogram. I don't think the ballistocardiogram will impact that much the envelope, let's say, in the alpha band. It will a bit, but I don't know. Right? And I would like to see inside and outside the scanner to have to confirm this. That would be a possibility.
Yeah, for the record that we currently have, we didn't, because like it was very heavy protocol and we had to be time locked, like be on time moving into the scanner. We couldn't record outside the scanner, just record it inside the scanner. So we don't have that for now.
Yeah, no, but I mentioned that because you have the stuff plugged all day, so you don't need to record too long. If you can, that would, yeah.
So, maybe we can start. So
Yeah.
we are going to invite, Christophe and Ms. to discuss your result.